physicist, a couple 100 years ago, and he did that thing of making a really simple observation that had really profound implications. And in fact, the stuff that Doppler did is really the foundations for Einstein's special theory of relativity, not the general theory, but the special theory of relativity. So really important stuff. And his observation was that if we are watching something happening, it'll look different to us if we're standing still or if we're moving. And you're very familiar with that concept, because usually, maybe not this Friday, maybe not today, but usually on a Friday, you'll get to the end of the day, you'll be desperate to get home, and you'll do the thing you're not allowed to do, won't you? You'll do that thing of cutting out the back of the hospital through the emergency departments to get to your car quickly. You're not allowed to do that. And as you do that, just as you go to step off the pavement, you hear a siren. And you can know without looking whether or not it's safe to step off and keep walking. Because if what you hear is a siren with that very high-pitched, urgent sound, you know the ambulance is coming towards you and you better step back. On the other hand, if you hear that more low-pitched, relaxed siren, you know it's going away from you, so you can continue walking. You don't have to, you can tell just by listening. Now, that's not because the ambulance has got two different sirens. It's because of the Doppler effect. And the Doppler effect depends on the thing we said earlier on, which is that once you've chosen a wave and chosen a medium, the speed is fixed. So if you choose a sound wave in air, say for this siren, a sound wave in air, then it will move at 330 meters per second. You cannot change that. So imagine I'm the ambulance and you're about to step off. So I'm actually parked with my siren going. Nino, Nino, Nino. Yep. And you're hearing. So what do you hear? Well, I'll send off the first knee and it'll move towards you. Then I'll send off a gnaw and it'll move towards you. And I sent them off that far apart, so with that frequency and wavelength. And they arrive with you with the same frequency and wavelength. So I think I'm saying Nino, Nino, and you hear Nino, Nino. Very easy. We're both sitting still. What, however, if I'm moving towards you? If I'm moving towards you, then you set off the first knee. And now it's time to send off the gnaw. But I've chased after it. I've moved towards you. So send off the gnaw here. And look, they're much closer together. So I thought I was setting them off this far apart. But because the first one left me and moved at 330 meters per second, and I couldn't change that speed, I caught up with it. And when I set off the second one, they're much closer together. So I thought I was sending off a Nino, Nino with that frequency and wavelength. But you hear a Nino, Nino, much higher pitched, higher frequency sound arrive with you, because the wavelets that arrive with you are this close together because I was chasing after it. So because I'm moving, you hear something different than I think I'm making. So I think I'm making Nino, Nino, you hear Nino, Nino. The other thing I'm not very good at is singing. So drawing and singing are not my fortes, as you've gathered. What if I'm moving away from you? I said the first one, the first knee, is moving at 330 meters per second towards you. It's time to set off the gnaw, but I've moved away from you. So now they're really far apart. So I think I'm sending off Nino, Nino, but you hear Nino, Nino, much further apart because I've moved away from you. So I think I'm sending one frequency and you hear a different frequency. That's the Doppler effect. And that's why when you step off the pavement and outside casualty, you can tell if the ambulance is moving towards you or away from you. The faster I'm moving, the bigger that change. So the Doppler frequency is actually the change in frequency between what I think I'm sending, but between what I'm sending and what you hear. So the difference between the received frequency and the transmitted frequency, that's a Doppler frequency. And the Doppler frequency is related to the speed of movement. There's a formula that describes it. You won't need to use the formula. That's just an image of a police car and how I always feel when I see a police car when I'm driving. You know, if both are stationary, then you both hear the same frequency. If the car's moving towards you, you hear a higher frequency than he thinks he's making. Because there are no police cars or ambulances inside us, but what there are red blood cells, and exactly this happens from red blood cells. When the instant wave hits the red blood cell, it scatters in all directions, like we said earlier on. If the red blood cell is sitting still, the scattered wave's got the same wavelength and frequency as the instant wave. If it's moving towards you, the waves pile up, so you get a higher frequency. If it's moving away from you, the waves stretch out, so you get a lower frequency. So with Doppler, you send off a beep, and you listen to hear, do you get a beep back, in which case nothing's moving? Do you get a beep back, in which case something's moving towards you? Or do you get a beep back, in which case something's moving away from you? So you listen to the frequency of the reflected of the returning wave, whether it's reflected or scattered. You listen to the frequency of the returning wave and compare it to the frequency of the outgoing wave, and that tells you how quickly this red blood cell is moving. So by listening to the received frequency and knowing the transmitted frequency, you can calculate the speed of, or estimate the speed of movement. So that what you get from Doppler is a Doppler curve. They always look a bit scary, don't they? But in fact, what are they? They're just speed time graphs. And the things you do with speed time graphs are exactly the same things you do with speed time graphs when you're doing O-grade maths and you drew these speed time graphs and calculated the area underneath them to find the distance traveled and so on. It's exactly the same things we're going to do with the Doppler curves. They're just speed time graphs of usually the blood moving. Okay, so that's the principle of Doppler. There's a catch. What if? So back to traffic policeman again. Now I'm a traffic policeman. I'm not coming towards you. I'm not going away from you, but I'm driving past you like this. Yeah, I've got a curl in my lip because I've always got a curl in my lip. I've got a really big belly, even bigger than mine. You know, I've got a big belly, curl in my lip, traffic policeman driving past. I've got my siren on because I like the attention. Nina, Nina, Nina. What are you going to hear? I'm sending off Nina, Nina, Nina. Now, I'm not moving towards you, so the waves won't pile up because I'm just driving across the street. I'm not moving away from you, so the waves won't stretch out. So those will stay the same distance apart. So that I'll send off a Nina, Nina, and you'll hear a Nina, Nina. You say, therefore, the instant wave and the return wave got the same frequency, therefore the speed of motion is 0. But clearly the speed of motion is not 0 because you watched me go across your screen like that. So what does that tell you? Doppler only allows you to calculate speeds towards and away from the probe, and you know that. So that if you move in a different way, such as, I'll show you here with the whiteboard for a second. I might add a page thing. Add a blank page. There we go. So if you think here's the probe, you can only measure speeds in that direction. What if you're going in that direction? Oops, slightly missed the probe. Make it a fatter probe. What if you come in that direction? Well, what you have to do is you have to say, well, it's back in the telly, isn't it? That ridiculous program I hate, Strictly Come Dancing. You know, you can either go diagonally across the screen like this, which is what is actually happening, or you can go side together, side, one step forward, can't you? You end up in the same place. So that's to say, this motion here, you can split into 2 bits. This bit plus this bit, just like they do in Strictly. Yep. And when you try and measure using Doppler, this bit you cannot measure, and this bit you can measure. So if you want to measure V, you try and measure it, what we actually measure. You won't measure this bit, but you will measure this bit here. And if that angle there is theta, remember, do you remember SOHCAHTOA from O-grade math? SOHCAHTOA, cosines adjacent over hypotenuse. So cosine of this angle is adjacent over hypotenuse. So what you actually measure is V cosine theta. And that means if you think what the cosine graph looks like, the cosine graph looks like that between 0 and 90 degrees. So if you're around here, cos theta is around 1. But once you get past 20 degrees, it becomes, 0.8, 0.6, 0.5. And you start measuring half the value you should be measuring. So you've got to be within 15 or 20 degrees of the direction towards the probe to make it a reliable measurement of this, ideally straight towards the probe. Okay. Back to the slides. We've talked about that. So there are three flavors of Doppler. One is continuous wave. What does continuous wave mean? It means you take your probe. You know how much probes cost? Typically, a probe for a standard machine will cost 20 grand. That's probably not fair, between 10 and 20 grand. And I know because we'll keep breaking them. Essentially, press CW. What it does is it saws your 20 grand probe in half down the middle like that, to two separate halves. One half transmits all the time. Another half listens all the time. So one half transmits, sends out a wave that just is like, it goes on and on and on and on and never stops. Another half just listens all the time and says, am I hearing a da coming back? Or is it dee coming back? Or da coming back? Just listens all the time. So that wave never stops and therefore never starts. And how do you know where something came from on the screen? It's because you timed how long it took to leave the probe to get back to the probe. So that means if it never starts, you can never start your timer. So you can never know how long it took to get to the reflecting surface and back. So you can never know where it came from because you can't time. So continuous wave, you don't know where down the line the signal has come from. You don't know where the velocities come from, but you can measure any change in pitch. So you can measure any speed. So continuous wave, half the probe transmits, half receives. You can't time, so you can't know where it comes from. You can measure any change in frequency, so therefore I can measure any speed. And what you get from it, you get a speed time graph of the blood flow down the line you've chosen. But like these. Remember, stop thinking about these like Doppler curves. Remember, they're just speed time graphs like you had at school. Duplex is the mode where you get the Doppler curve, but the grayscale image at the top moves. You've seen that, haven't you? So I mentioned that, first of all, to tell you what duplex Doppler is, and secondly, to tell you it's a really bad thing. It's a great thing for lining up where to put your probe and your sample box, but it's a really bad thing for making measurements, because to get even a small grayscale image, it still takes 40 lines to get it, and then you can have a few lines down to measure the speed, and then another 40 lines to take the next grayscale image. So you use most of your processing power making the grayscale image, and hardly any taking the Doppler image. Therefore, you get poor quality Doppler images. And so what you need to do is you need to use duplex to set things up, then switch duplex off so the grayscale image freezes, and you get a much higher quality Doppler curve. If you submit a case in your CD of cases for the practical assessment, if you submit a case with the duplex mode on and make a Doppler measurement from it, you'll fail that whole case on the basis of that alone. So it's something that's viewed as a really bad thing to do, and quite rightly too. So that was CW, that's continuous wave. Pulsed wave. So you say, well, if I don't know where it's coming from down this line, why do I not stop making a continuous noise and go back to making a bit of ultrasound? Set up a bit of ultrasound and then wait to see, say I'm interested in here's my probe, and here's the thing I'm interested in, how fast it's moving. I know it takes 1, 2, 3 seconds to get there, another 3 seconds to get back to the probe. So why don't I just set up a bit of ultrasound, wait 6 seconds, and then listen to the noise that I get back. Beep, bop, boop. And that will tell me how it's moving. And then I'll know about speed. And then I will know about speed, and I'll know about position as well. There must be a catch, because otherwise that's all we do. And you can see the catch immediately, because just think about what we described. You set up a bit of ultrasound, and then you do nothing for 6 seconds until that bit comes back. So the machine is effectively switched off for 6 seconds, doing nothing. And during that time, anything could happen and you'd never know about it. So the problem with pulsed wave is, you can see the speed now, but between those little samples, you've got no idea what the hand was doing. You've got no idea if it was sitting still or if it was moving backwards and forwards. And every time you sent a pulse, just happened to be there. So you don't see this bit in the middle. And that's the problem with pulsed wave. It's a bit like this. If you watch my arm, yep. So just watch it. It went round in a circle. Yep. That's continuous wave. You watched the whole thing. You've got no doubt what happened. Pulsed wave, we've just said, is you just get little snapshots. So I'm going to demonstrate that by getting you to, I've got no way of knowing if you're doing it or not, but I'm going to trust you. I'm getting you to open and close your eyes when I tell you, and then you'll see just little snapshots. Yep. So open your eyes, close, open, close, open, close, open, close, open, close, open, close, open. Now there you saw lots. You saw my hand here, 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 here. So you said, well, what I saw was your arm doing that. And you were correct. Here's another one. Open, closed. Open, closed. Open, closed, open. Now this time, it's a bit more jerky, wasn't it? You saw my hand here, 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 and here. And you said, well, probably what happened was I saw your hand doing that. And you were correct. But it's jerky. You had to make a bigger guess that time. One last time. Open, closed. Open, closed. Open, closed. Open. So this time, what did you see? You saw a hand here. You saw it here. You saw it here. And you saw it here. So what is your... So here, then here, then here, then here. What does your mind reconstruct? It doesn't reconstruct my hand doing that to get to this position. It said, which is the first time you saw it, it says probably what your hand has done is that. You saw it there, and you next saw it there, and you next saw it there. So you come to the wrong conclusion. you came to the conclusion that my arm was doing this. And it wasn't. It did that again. Because you weren't looking often enough, you got it wrong. And that's aliasing. You get it wrong because you're not looking often enough. So that's what aliasing is. And to get it right, you got it right when you first looked before I got to halfway. Yep. The last example, the first time you looked was after I got to halfway and you got it wrong. So you could rephrase that by saying, you'll get it right if you look twice in a circle. So that's the first time you look is before halfway. And you get it wrong if you look less than twice in a circle. So to avoid aliasing, you need to look twice as often as I'm rotating. So your observational frequency has to be more than twice the needs to be more than twice the thing you're trying to measure. So and what do you call how often you look during Doppler? You call it the pulse repetition frequency. So it has to be at least twice the thing you're trying to measure, which is the Doppler frequency, isn't it? So your pulse repetition frequency has to be at least twice the Doppler frequency. And that's where that formula comes from. It tells you about aliasing, isn't it? Okay, so that's aliasing. That's a common question. I've got some questions about it tomorrow, so we'll come back to it. But aliasing means you get the wrong answer. It's that thing where you disappear off the top of the screen, come back at the bottom of the screen, and can wrap round and round and round. So somebody said, can we miss any defect in pulse wave Doppler? So the answer is yes. We just described exactly that you know, you can't measure high Doppler frequencies with pulse wave Doppler. So continuous wave Doppler allows you to measure any speed, but you don't know where it comes from. Pulse wave Doppler allows you to measure, it allows you to know exactly where it's come from, but you can only measure a Doppler frequency of half the pulse repetition frequency. So that means you can only measure low speeds. So pulse Doppler, you can only measure low speeds, but you know where it comes from. Continuous, you can measure any speed, but you've no idea where it comes from. So that's CW and PW and aliasing. And the last kind of Doppler is color Doppler. Color Doppler, it's a picture. This is because you can't increase the PRF enough in pulse Doppler. So yes, there's a limit to the PRF. And in fact, there's a question about that tomorrow. So I'm not going to talk about what the limit is to the PRF today. But the limit is just distance equals speed times time, is because it takes a finite amount of time to get to the sample volume and back. We'll talk about that tomorrow. And you can't send the next pulse down the line until the first one's got back. So you send the first one down, you've got to wait till the first pulse gets back before you can send the next one down. So high PRF is something else. That's a trick, and is not a different technique, but it's something we'll talk about tomorrow. So it may help take away some of the aliasing, but you introduce other problems. So high PRF is a topic for tomorrow rather than today. So the things you should be taking away from today is thinking about aliasing, what pulse repetition frequency is, and the difference between pulse and continuous wave, and color Doppler. Color Doppler is just a picture of the speed of the blood moving. And that picture is set up so that anything that's coloured blue is moving away from the probe, and anything that's moving coloured red is moving towards the probe. It's a picture of the speed, not the volume. So it's not a picture of flow, it's a picture of speed. And gives you an overview really, and tells you where to look with your pulsed wave and continuous wave to find an abnormality. I just want to, I'm not going to go through it all because you're very familiar with all of these, but I just want to show you what very familiar with what it looks like and so on. I just want to show you this, not because of variance. Variance is just how much difference, how much range of velocity there is within the sample. It's not because of that. But just look at this. What is this? You know what this is. This is aortic regurgitation. This is a picture of the aortic regurgitation jet. What are you thinking? What's going through your mind as you look at this? Hopefully, what's going through your mind is, bloody hell, why am I wasting my Friday morning listening to this chump? Because he clearly doesn't know what he's talking about. I hope that's what you're thinking. Because he's just spent 15 minutes telling me that with Doppler, all I can see is movement away from the probe and towards the probe, and then he's gone and shown me a picture of movement across the screen. He clearly hasn't got a clue what he's talking about. I hope that's what he's thinking, because that's what you should be thinking, because this is absolutely unexpected, isn't it? We're using a Doppler technique, and we're coming up with a picture of motion across the screen. How can that be? How can that be? That can't happen, can it? And it's because, very importantly, color Doppler is not just Doppler. Color Doppler is a complicated, multi-measurement, statistically analyzed picture, an averaged picture of what's going on. And essentially, it compares in different pixels the velocities and comes up with whether or not there's likely to be velocity in other directions, such as moving across the screen. That process is called autocorrelation. So you should know several things. You should know that actually color Doppler is not color Doppler. You should know that you can visualize things that don't just move towards and away from the probe. And that's because it's a complicated statistical analysis called autocorrelation is going on in the background. And autocorrelation is a kind of averaging process. So that if you were to try and extract the numbers, because you can see the scale on the side, you know, the 50 and minus 50 plus 50 or whatever. If you were to try and extract the numbers, those numbers are different from the numbers that appear on the spectral speed time graphs, because they're the real numbers. These numbers here are highly averaged numbers. So you just need to be aware that color Doppler is useful as an overview, but it's not just Doppler. It's a complicated statistical thing called autocorrelation. Okay. There's lots of questions about artifacts later. Okay. I'm going to, sorry, just one second. So I'm going to move on from physics then, unless MD has got any questions. Okay, so I said already, high PRF is a topic for tomorrow, and we will mention that tomorrow. I'm not going to mention that today. And you can't tell in high PRF where the velocity is coming from. You just know it's coming from one of the two sample volumes. You cannot tell which one it's coming from. But we'll talk more about that tomorrow. Okay. For the next thing I want to talk about is calculations. And I think I just want to use the whiteboard for this. You've got the slides, but I'll just use the whiteboard rather than show you the slides for this one. Add blank page. There we go. Okay. So sometimes in the exam, there are no calculations to do. I think, and it's a guess or an estimate, but I think in about 2/3 of the exams, there are no calculations to do. And in about 1/3 of the exams, you'll be asked to do a calculation. You won't be asked to do a complex calculation. So it's very, very, very vanishingly unlikely, for example, you'd be asked to calculate a regurgitant volume. for example. You might be asked to do a continuity equation. Once, a long time ago, there was a reported to be a question where you had to calculate a PISA and effective production orifice area. To the best of my knowledge, that's not recurred, and I suspect that's because nobody could do it, so it wasn't a helpful question. So what I plan to do is just take 10 or 15 minutes to show you the basics of the calculations that you can apply, because the principle is the same in lots of different situations. So show you the base of the calculations, and then you can apply those. Whether or not you'll need to do them, I don't know. Of course, I don't know. But statistically, the chance is about, I think, about 30% when you do a calculation. So the first calculation is stroke volume. So that's easy. So it's really depressing. I need to wear my specs to see properly these days. It doesn't make my drawing any better. So here's where we are. So we're during systole, and the aortic valve's open, the mitral valve's closed, and blood is flowing out the heart. And it's going through the left ventricular outflow tract. And what we want to know is what volume of blood comes out each time the heart contracts. That's what you want to know. You want to know the stroke volume. So what you'll see is the blood's forced through here, and then you imagine, forget everything else, just imagine as the blood's forced through here, it'll make a cylinder, and it'll make like a stick of rock that comes out through the left ventricular outflow tract, won't it? So you can think about this just like making a stick of rock. What's the volume of a stick of rock? The volume of a stick of rock is the volume of a cylinder. So it's the cross-sectional area times the length. So how are you going to find that? Well, the cross-sectional area is just the area of the left ventricular outflow tract. And as you know, you can, it's not easy, but you can measure the diameter of the left ventricular outflow tract. So what you've measured then is the diameter of this thing that you presume is a circle. Mistake number one, presuming it's a circle. Mistake number two, knowing where this starts and ends, that that can be really difficult, particularly if it's abnormal aortic valve. But you know this diameter. And then for a circle, if you know the diameter is d, what's the area? The area of a circle is pi r squared. That's the same thing as pi d squared over 4, which is the same thing as 0.718 d squared. All these things are exactly the same formula. So you can calculate this area. Once you know the diameter, you can calculate this area easily. So that bit's easy. How do you find the length of the cylinder? Well, the length of the cylinder is, as the heart squeezes, is how far this red blood cell moves, isn't it? How on earth are you going to manage that? Remember, your probe is here. That motion is going across the screen, so you're not going to be able to see that with anything apart from coloured Doppler, so that's no use. So you need to go, as you know, round to a 5-chamber view. Something like that. And you need to put your probe in the same position as it is here. So you need to measure how far away from the aortic valve you are, typically around 5 millimeters. Have that same 5 millimeter gap here from the aortic valve, and put your probe here, your pulse wave probe here, and then you get, from that, you get a speed time graph, the blood going out. Speed time graph. It's probably 0.785. I can't actually remember. I never use it. Yeah, you're probably right. It's 0.785. It's whatever 3.14 divided by 4 is. So 3.14 is going to be more than 0.75. So it's going to be 0.785. You're right. But that number is just 3.14 divided by 4. Thanks. Sorry. So you get a speed time graph that looks like this. And that's a speed time graph of that red blood cell moving out now in the same direction as towards and away from the probe. So now you can measure it. So that's a speed time graph of this red blood cell moving here. If you go back to O-grade maths, you remember doing this. Mr. Brown gets into his car, he accelerates to 30 miles an hour. He drives at 30 miles an hour for 10 minutes and then slows down again to stop. How far has he traveled? You say the distance traveled, and the speed time graph, the distance traveled is the area under the graph. You remember splitting that up into triangles and squares, calculating the area of each one, and then adding them together. We do exactly the same for this speed time graph. It's called the Doppler curve. You're going to calculate the area underneath the curve, and the area underneath the curve is the distance traveled. So distance traveled is area under speed time graph. Of course, you don't call it distance traveled because that would be far too clear. You call it something like velocity time integral. And that will tell you, or stroke distance is sometimes what you call it. And that area there will tell you the distance traveled here. So that's how you calculate the stroke volume. It's the volume of this cylinder of blood that comes out, the stick of rock of blood that comes out. This comes from the cross-sectional area. This comes from the LVOT diameter to calculate cross-sectional area. And this comes from the Doppler curve taken from a different image. So lots of potential for abnormalities. So that, first of all, is that's the volume calculation, the standard volume calculation for either the left ventricular outflow tract or the right ventricular outflow tract, or inflows indeed, although you don't tend to use it so much there. Okay, what's the continuity equation? The continuity equation is used usually when you've got aortic stenosis, for example, and you've got the left ventricular outflow tract here, and here you've got your aortic valve, which now only opens a little bit like that. So as the heart squeezes, the blood gets forced out of here. It goes through the left ventricular outflow tract. So that gives you a cylinder of blood like that. And then, because this only occurs during systole, only involves systole, everything that goes through here must then get pushed through this second hole. So it gives you a much smaller but longer stick of rock. And these two must have the same volume, because everything that goes through here as the heart squeezes must come out through there. So this is what we just talked about before, pi d squared over 4 times the LVOT VTI, which we got from pulsed wave. What's this? Well, this area here, that's the aortic valve effective orifice area. And this distance here is what? Well, that's how far the red blood cell that's here moves. How do you get that? You go back around to the apical 5 chamber view, but what you take this time is you take the CW. The CW will give you the movement with the highest speed, and the highest speed is going to be the movement through the narrowest point, which is through the stenosed aortic valve. So this time, to get the aortic valve VTI, you take it with CW, and you get this curve. You calculate the area under this curve, and that gives you this distance here. So that's the continuity equation, which is really just applying the volume equation twice. What else can you do? You can apply again the volume equation in a different scenario, which is here. So you might, in this case, you might have a young chap or lady where you're looking at the right ventricle and the left, that's the left ventricle on the left and the right ventricle on the right. You're looking at them in systole. And you might say, well, I can calculate the left ventricular stroke volume, because that's just pi d squared over 4 times the LVOT VTI. But I can do exactly the same thing for the right heart. So you can calculate the right ventricular stroke volume, which is just the diameter here, call it the right diameter or something, pi d squared over 4 times the RVOT VTI, which you can actually get from the same image just by putting your pulse wave box there. In this case, you ask the question, are they the same? That is to say, is there an intracardiac shunt or not? So this is different. In this case, the continuity equation, you insisted that they're the same. Here, you say they may or may not be the same. If they're the same, it's probably a normal heart. If there's different, then there might be an intracardiac shunt. So again, you're just using the same calculation as the first time in a different scenario. So those all represent essentially the same calculation, that stick of rock calculation used in different ways. PISA, I think you're really unlikely to get asked to calculate. I would mention it, and there's one question tomorrow, just because it came up once. I think it's unlikely that's going to come up again. As time goes by, it becomes less likely. But essentially, there's the mitral valve. It should be closed, but there's a hole in it during systole, which allows mitral regurgitation to flow from the atrium to the ventricle. And that blood flowing through here has to queue up to get in. And when it comes out, it gets forced through there in a thin stick of rock. Now then, we talked about the continuity equation a second ago. We said volume through the LVOT equals volume through the aortic valve. And that's great, that works. What about if we said not volume, but instantaneous flow? That is, the volume per second has to be the same, because there's no place for it to go. What goes in must be coming out at the same rate. So if we said, rather than a continuity equation, we're going to have a flow rate equation, saying the flow in has to be the flow out, that just means volume per second in equals volume per second out. So that's another kind of continuity equation. It's the same as substituting, instead of the VTIs in the continuity equation, substituting the velocities in their place, which you can do if you're not given the VTI in the exam. And I've got a couple of examples of that tomorrow, just to remind you of that. So the continuity equation should be the VTI. If you've not got the VTI, you can use the velocity. PISA, you've got to use the velocity. It's an instantaneous flow equation. So what's coming in? So what's coming in is the flow is all coming into this defect, and the shape that I've drawn is half a football, because it's a three-dimensional shape. It's half a football. You won't know this, but the area of half a football is 2 pi r squared. You don't need to know that. Well, that's not true. I don't expect you to have known that off the top of your head. So that's the area here. How fast is the blood moving here? Well, you know that because you can just look at the box on the side of your screen. It will tell you what the velocity ranges are. And usually, typically, you'll set this to be 40 centimeters per second, which is the aliasing velocity, isn't it? So what's coming in per second is, so what we want is volume per second. So area times velocity gives you volume per second. So what's coming in per second is 2 pi r squared, that's the area, times the aliasing velocity, this 40 usually. So that's what's coming into here per second. What's coming out of here per second? Well, it's a stick of rock. The area is the mitral valve effective orifice area. And the speed it's coming out with is the maximal speed of the mitral regurgitation. So this is an instantaneous flow equation. It's an instantaneous continuity equation or flow equation, or whatever you want to call it. And what comes, there's no place else for it to go. So what comes in here must go out through that gap. So these two things must be equal. In must equal out. So the Pisa equation is 2 pi r squared times the Ellising velocity is the thing you want to know. Mitral valve effective orifice area times the MR velocity. So that's the Pisa equation. I think you're relatively unlikely to be asked that. And then the last calculation that you're much more likely to be asked about is that if you've got a small hole causing a regurgitant jet. Now, that doesn't have to be in the tricuspid valve. It can be in the mitral valve, it can be in the aortic valve, it can be in the interatrial septum. It can be in interventricular septum. It can be any place with a small hole with that pressure difference pushing blood through it. So it's got to be a small hole, so a restrictive defect for the equation to work that says the pressure difference is roughly 4 times the velocity squared. You'll be very familiar with that modified Bernoulli equation. So there's two things about it. First thing is, it doesn't just apply to the tricuspid valve, which is where it's most commonly used. You can apply it to any place where there's a small hole. And I've got a question in one of the exams we do at home where you have to trace pressures through mitral valve regurgitation, through a small VSD, through tricuspid regurgitation to compare the atrial pressures. So it doesn't just work there. So first of all, the first thing to know is this modified Bernoulli equation doesn't just work there. Second thing to know is don't remember the equation in this form because you're likely to get it wrong. What you need to remember for the purposes of the exam is this. You'll remember that V1 is the velocity, for example, in the LVOT. It's the velocity just before the stenosis. So this is V1 here, this is V2 here. Normally, all you need to do is square this unless this is high. For the purposes of the exam, remember the formula in this form. If you are given V1 in the exam, so the LVOT velocity most commonly, if you're given it, use it. If you're not given it, you can't use it. So I don't think you have to make a qualitative judgment of whether to use it or not in the exam. The rule should be, if you're told information, use it in this formula. If you're not told information, just use 4v squared. But you'll always get it right if you remember the bottom form of the equation for the exam rather than the top form. Okay, that's all I wanted to talk about. That's all I wanted to talk about calculations. I think there's a reasonable chance you'll be asked to do that. Okay, let me stop sharing and bring up the next talk. Do we need to adjust aliasing velocity for Pisa in direction of a regurgitant jet? I'm not sure I understand the question. You need to have so generally you want to make the Pisa big, so you want to adjust the aliasing velocity either by raising the baseline or reducing the scale so that alias is about 40 centimeters per second. But yeah. Okay. And the reason you do that is because you want the pieces to be big, because it's easier to measure big things rather than small things. So you, by reducing the aliasing velocity, you by reducing the aliasing velocity, you make the pieces bigger. Good. Okay. So deformation imaging. This is a bit of a nuisance. This is a bit of a nuisance because essentially it's something you're not going to use in clinical practice. Use a tiny amount of tissue Doppler in one specific situation, as you know, but apart from that, it doesn't really form part of clinical practice. However, it definitely does form a part of the syllabus for this exam, and it has cropped up intermittently in the exam. And it seems to me that that's a really outrageous thing, but it doesn't matter, I think, because you know, I'm not writing an exam, you're doing an exam, you've got to answer whatever questions you're asked of. So we've got half an hour now talking about deformation imaging, which is tissue Doppler and speckle tracking. And you know, it's one of those things that you're probably not using in clinical practice, but might have to deal with in the exam. Excuse me. Okay. This is all about quantifying images, and we quantify images so that we reduce subjective variation between people. And this slide just is an example of subjective variation. When you first looked at this, it said if the group's big enough, then 40% of you will have seen a solid triangle pointing upwards. 40% of you will have seen as the first thing when you looked at it an open triangle pointing downwards, and 20% of you seen as the first thing we looked at as a six-pointed star. And the point being, we can all look at the same thing and see different things. I definitely see the solid triangles pointing upwards as the first thing we look at it every time, and I don't know what that means, if anything. So what we're going to talk about is deformation imaging, myocardial mechanics, whatever you want to call it. And really there is two bits to that. So how to think about this is, let me just show you how I think you should think about this. You want to describe the myocardial mechanics of the deformation. That means you want to describe the motion and contraction of small bits of muscle. So the power of this technique, or the important thing about this technique, is you can talk about small bits of muscle, because once you can talk about what a small bit of muscle is doing, you can add up all small bits of muscle and come up with something that describes the whole of the muscle. But the real power of it is if you choose to, you can deal with small bits of muscle at a time. If you talk about what a small bit of muscle does, what can it do? You need to know where it is. You need to know how fast it's moving. You need to know if it's contracting. And you need to know how quickly it's contracting. Is it contracting slowly, or is it contracting quickly? So those are the things you want to know in terms of your myocardial mechanics, or your deformation, or whatever you want to call it. You want to know about position. You want to know about speed. You want to know about contraction. Can somebody switch their microphone off? Whoever switched the microphone on, thanks. You want to know about contraction, and you want to know about speed of contraction. Contraction is called strain, and speed of contraction is called strain rate. So these are the things that you want to measure if you want to talk about deformation or myocardial mechanics. 1, 2, 3, 4. And there's two ways of measuring them. One is tissue Doppler, A tissue Doppler primarily measures speeds, and one is speckle tracking. As speckle tracking is predominantly about positions. From speeds, you can calculate strain rates, strain, and position. And from position, you can calculate speed, strain, and strain rate. So you can calculate them all, but from both tissue Doppler and speckle, tissue Doppler, the primary thing you measure is speed. Speckle, the primary thing you measure is position. So we talk about tissue Doppler first. All good stories, as you know, all good stories start in Scotland. And this story started in Scotland in the 1980s. And it started in Edinburgh. And really ridiculously, I picked this map off something. It doesn't show my hometown, which is just about here underneath where it says M9 in Falkirk. It started in Edinburgh with a chap called George Sutherland, who you may have heard of, who's been a cardiologist in many places in Europe and has spent quite a long time in London. And he was in Edinburgh as a research student in the 1980s, working with Professor McVickers, who's a physicist. And they said, can we measure myocardial motion? Can we measure how quickly, can we draw speed time graphs of how the muscle is moving? We are very good at drawing speed time graphs. Even in the 1980s, we're very good at drawing speed time graphs of how the blood moves. Can we take that principle and apply it to the myocardium? Well, if we just stop and think about it, blood, which we're good at, moves at a few meters per second, doesn't it? 1, 2, 3, 4 meters per second blood moves at. And blood is black. And blood is black because you don't get reflection from it. You get a little bit of scattering, which is low energy. So you get a low energy signal from blood that moves at high speed. So low intensity signal, high speed signal is what we're used to dealing with. If we want to measure how the myocardium moves, it is bright. So it is the opposite. It's a high intensity signal already. Can we? Somebody's still got their microphone on. Can I just I'll try and again from here, but can I ask you just to switch your microphones off if you've, because somebody keeps talking over me. So the myocardium is bright, so it's already high intensity, which is the opposite of the blood, which is low intensity, and it moves at not a few meters per second, but typically a few centimeters per second, so it moves much more slowly. So it's slow moving and bright, as opposed to blood, which is fast moving and dark. So what they said was, well, all we need to do is take the back off the echo machine, and where there was, so a high speed means a high Doppler frequency, which means in the signal we need to keep the high Doppler frequency, so we need a high pass filter, and it's dark, so we need a high amplification. If we want to use it for tissue, we just need to do the opposite to those things. Tissue moving slowly, so we have a low Doppler frequency, so we want a low pass filter, and we don't need to amplify it very much. It's already bright because it comes from reflection rather than scattering. So you swap a high pass filter for a low pass filter, lots of amplification, change it to little amplification, and we should get a Doppler trace of the myocardium moving. And that's what they did. And indeed, when you now press the TDI button on your echo machine, this is what happens. It swaps these things around, just like Professor Sutherland did in Edinburgh a long time ago with taking the back off the machine. And what you get is you get the ability to measure the movement of myocardium towards and away from the probe. And you generate speed time graphs like this. So this will be the speed time graph you're familiar with, because this is the one that you can use, as you know, to get the E primed wave. So this has put your sample volume just on the lateral annulus. So you're watching the lateral annulus. The lateral annulus, as you know, goes up during systole towards the apex, then comes down during diastole, pauses during diastasis, and then comes down again. So you've got three movements. You've got an upward movement, you get a down, pause, down. Back to Strictly Come Dancing again, isn't it? Up, down, pause, down. So velocity positive, first downward velocity, second downward velocity. And that's what you see in the speed time graph. You see the S wave, the first downward velocity is the E primed wave, the second downward velocity is the A primed wave. So we can draw speed time graphs of the tissue moving towards and away from the probe only. There's an image missing. Okay, so you can also do color tissue Doppler. But when you're doing this one, you get this with your arm wrapped around the patient. And if you take the probe off the patient, this disappears. So this is a real-time, high temporal resolution, because a single line, so maybe a temporal resolution of 1,000 per second. High temporal resolution, single line, live acquisition, spectral tissue Doppler. You can also take color tissue Doppler loop. So you take the color tissue Doppler loop. This is a segment, isn't it? So it'll be much lower temporal resolution. But you can store that loop and send the patient away. And once the patient's away, you can do this to the color Doppler loop and choose points and draw out the speed time graph of the movement. And you can see it's roughly the same. S wave, E primed wave, A primed wave. Got the same shape, very different temporal resolution. This temporal resolution might be, I don't know, 40, 50 frames per second. And has got a very different absolute number for the velocity, because this is color tissue Doppler. That's an averaging technique, so it gives you average velocities. So if you measure the lateral annulus S wave with this technique, you might get the number 6. And with this technique, you might get the number 8. They're both correct because they're measuring different things. This is measuring the true peak velocity, while this is measuring an average velocity. So you need to be careful. They measure different things and they're not interchangeable. And then with this kind of insight, you start to see really interesting things. So you see, for example, here, if you think about how the heart contracts, it doesn't do what you'd expect. Think about the apical 4-chamber view. If you're designing the heart, and here's the apex, and at the apex, there's nothing attached to the heart. And here's the base of the heart. What's at the base of the heart? Well, it's the aorta, there's the pulmonary artery, there's the 4 pulmonary veins, there's the SVC, there's the IVC, just to start with. Yep. So all these things attached to this end. Nothing attached to this end. If you're going to say the two ends need to move together, you're designing it, which end would you make move towards which end? You'd make the apex move towards the end with all the stuff, wouldn't you? You wouldn't make the heart, as it contracts, have to drag the aorta, pulmonary artery, the 4 pulmonary veins, the IVC, the SVC, with it as it contracted each time, would you? But actually, you know that's what happens, because in the 4-chamber view you're thinking about, you know, the apex stays next to the probe, and the mitral valve and the atria move up and down towards the apex. That's a really bizarre thing, but nonetheless, it's what happens. So think about splitting the apex, splitting the septum up into segments. The apical segment, therefore, you just described as fixed to the wall. Yep, so it's fixed here. So the apical segment will do this as it contracts. The mid segment will be making the same contraction, but because it's holding on to the apical segment, it's got to move much faster, even though it's doing the same amount of contracting. And the basal segment, because it's attached to middle segments, attached to the apical segment that's attached to the chest wall gets pulled loads. So it's really got to move a lot faster. So you can see, because of the configuration of the heart, that you expect the highest velocity to be at the base of the septum and the lower velocity to be towards the apex. That's exactly what you see here. Yellow is at the base of the septum and red is at the apex. The yellow velocities are much higher than the, than the red ones. So you start to see this idea of different velocities at different points, even the contraction is the same. So you start to see the really complicated way the heart moves in. These are mentioned, color anatomical M modes are mentioned specifically in the syllabus and cropped up once or maybe twice in the exam. I haven't featured for a long time. But when they did come in the exam, everybody looked at them and their jaws dropped open, I think, because they've never seen one before. So what's a color anatomical M mode? It is, you take a tissue Doppler image, like the one we've just looked at, and you draw a line that follows the shape of the myocardium. And you take that line and you straighten it out. So what you see on the y-axis here is numbers 1 to 8, and they correspond to the position in the myocardium, 1 being the base of the septum and 8 being the base of the lateral wall. The x-axis is time, and the color is whether it's moving towards or away from the probe at that position at that time. And actually, you know, these don't have to show velocity. They can show strain, they can show strain rate, they can show position, they can show lots of things. Most commonly velocity. And when you look at them, the thing you're looking for is symmetry. So is this symmetrical? And can you find a line of symmetry? And actually, the horizontal line that goes through number 4, something like that, is about a line of symmetry, isn't it? Almost. Apart from that, flashes of red and blue. Can you explain that? So between 3 and 4, or between 3 and 5, there are flashes of red and blue that don't exactly match symmetrically. Can you explain that? And the answer is yes, you can. Yes, you can explain that, because what's happening is 3, 4, and 5 are at the apex. At the apex, there's not much movement, so it'll flick between red and blue because, you know, you're at one side, the other side of 0, not far away from it, and you get a bit of random movement. So it makes sense that the bit around 3, 4, 5 doesn't show you much because it's measuring velocity, and the velocity there is low, but the rest of it looks symmetrical. So that looks normal. And if you see a lack of symmetry in these color anatomical M modes, what that means is that's the point that you should look at to try and identify the abnormality. Tissue tracking is a very similar thing. I mentioned this again just because it cropped up once in the exam. It hasn't cropped up since, to the best of my knowledge. Tissue tracking, the guys who did the exam were absolutely clear there's a question on tissue tracking, and that was the phrase that was used, which is a bit surprising because tissue tracking is a GE proprietary name, but nonetheless, that's what they said was used. And essentially what tissue tracking does is, for each segment, it uses tissue Doppler to calculate how far that segment moves during systole, how far upwards it moves during systole, and then color codes it, how far up it's moved according to the scale at the side there. And what you should see in a normal heart is symmetrical bands up and down up and down both walls. They're not quite matched, they shouldn't be quite matched, because the lateral wall, which is a free wall, moves more than the septum, which is tied to lots of things. So you see more movement in the free, slightly more movement in the free wall than the septum, but otherwise they should match, and there should be symmetrical bands across the left ventricle. So that's movement with tissue Doppler. Deformation, That is to say, contraction or relaxation. You need to watch these next two slides really carefully. That's movement. That's easy. That's deformation. And the reason you need to watch that slide really carefully is it took me ages to make PowerPoint do that, or Keynote do that. It took me ages and ages for some reason. Anyway, so I'm very proud of that slide. I'm just going to show you again. That's deformation. Deformation is a change in length, either a relaxation or a contraction. And the measurement of that is called strain. So strain just means the measurement of contraction. It's nothing to do with cardiologists. This was engineering concepts been around for a long time. Engineers had to worry about what would happen to the Empire State Building when King Kong jumped on it. Of course, what happens when a big load presses down the Empire State Building, it gets a little bit shorter, doesn't it? So the change in length. So a change in length is a change in strain. So strain is in this case is a change in length, a change in height of the Empire State Building. And the load that's causing it is called the stress, and that's King Kong. For something simple or relatively simple, like a one-dimensional building, you can relate the load to the change in height quite easily using something called Young's modulus. Unfortunately, you can't do that with the heart because it's too complex. Okay, so strain is strain is easy to think about like this. It's simply the change in length. So something starts off at 8 centimeters long, ends up 14 centimeters long. It's got bigger by how much? It got bigger by 6 centimeters. It started off at 8 centimeters, got bigger by 6. It started off 8, so 6 over 8. It's got longer by 75% because 6 over 8 is 75%. So strain is just a percentage change in length. That's all strain is. And strain rate is just how quickly it changes. So if this change happened over 1 second, strain rate would be 75% per second. If it happened over 3 seconds, each second is a 25% change. So the strain rate would be 25% per second. So strain is just a percentage. Strain rate is just how many percentage change there is each second. So the units are per second. And one thing you're used to measuring, which is just a change in length, is wall thickening. It's this idea of wall thickening that you've been used to since you were, first saw an echo machine. It's just the same thing as strain. Again, it's a change in length of the myocardium in a different direction. Ugh. And then, how do you measure that how do you measure a change in length with tissue Doppler? Well, to measure change in length, up until now, we've measured 1 point and how much it's moving, how quickly it's moving. To measure change in length, you need a chunk of muscle, so it's got 2 ends. So you need 2 points, a point at one end, a point at the other end. And what you do is you compare their speeds. So if they're moving at the same speed, the length's staying the same. This speed is the same as this speed. If this speed is higher than this speed, then what will happen is the bar will get longer. So you compare the speeds. If this one's higher, the bar is going to get longer. If this one's slower, the chunk of muscle or the bar or whatever it's going to get shorter. So to calculate strain from tissue Doppler, you compare 2 speeds, see how different they are, and that tells you about how much change in length there's going to be. That's sometimes called the myocardial velocity gradient, because what you're doing is saying, is the speed here the same or different than the speed here a centimetre away, or however far away you're interested in. So you're comparing speeds at different points in the myocardium, so you sometimes call it the myocardial velocity gradient, is the phrase that's used. So that's how you do it with tissue Doppler. What about speckle tracking? Speckle tracking is intuitively much easier to understand. If you look at any 2D image, you always see speckles, don't you? Sometimes they look brighter. You can turn the gain up, look bright. Sometimes they look less marked, but you can always see them. And not just if you think there's amyloid. So imagine you walk into the pub tonight and you see me. How are you going to know that you've seen me? How are you going to recognize me? You're going to look at me, look at my face and head, and say, I recognize that face and that head. Therefore, that's Grant. Therefore, I know that whole person is Grant. And you use my face, and in particular my face and head, as a sort of label. And if you recognize this, you know that belongs to me. And the question is, if you look at the speckle pattern, which appears to be different, as you can see in this slide, at different points in the myocardium, can I use that pattern as a sort of label to say, I recognize that pattern, therefore I know it's that bit of myocardium. So can you use that in the same way as you use my face to recognize me? Can you use that speckle pattern to recognize that bit of myocardium? So it acts as a label. The answer is obviously yes, because otherwise we wouldn't be talking about it. So how does it work? So we just go back to basics just for a moment. As we've said already, as you know, a wave goes through a medium, it attenuates. And it attenuates because it loses energy. It loses energy because it interacts with different bits of the medium. And you know, as it goes through, say, the septum there that we're just looking at, there's lots of myocardial fibrils, there's lots of very small blood vessels and other stuff that form part of the ultrastructure of the myocardium. And as the wave hits these small things, it scatters. So you get lots of scattering just as the wave progresses through the normal myocardium. And of course, the arrangement of those things at the base will be different from the mid, different from the apex. It's a sort of random thing, isn't it? So you get sort of random scattering within different bits of the myocardium. So you get lots of low energy waves going in all directions, which inevitably will bump into each other. And what happens when waves bump into each other? They interfere. And what happens depends on how in phase or out of phase they are. So if they are out of phase, like the blue image at the top, so a peak bumps into a trough and a trough bumps into a peak, they cancel out and you're left with nothing. So you're left with blackness. If a peak bumps into a peak, such as in the white image at the bottom, and a trough bumps into a trough, then you get big peaks and big troughs, and that gives you a very bright image. If it's something in the middle, you get a bit of greyness. So as they interfere, they'll give you bright areas, dark areas, and grey areas. Here's an example of just two things, like the kids dipping their two fingers in the bath, two sources of a wave which are in phase, giving you a very predictable interference pattern with you can see the bright, the dark, and the grey there. And if they're random scatterers, they'll give you a different pattern. It's not unpredictable, but a fixed pattern. And it's this pattern that forms the speckles in the myocardium. It's this random scattering leading to interference, leading to a fixed pattern of brightness that are the speckles. So that's why you've got the speckles. That's why they look different at different bits of the myocardium, and why it's reasonable to use them as a label for that bit of myocardium. And indeed, if you watch how the myocardium moves, then you can see that each speckle moves absolutely in line with the base, suggesting that they're all moving with the myocardium. Does speckle tracking then work? What it does is you choose the bit you're interested in, and then you set up a search area. So you choose the bit you're interested in here, which is the kernel, it's called. You then the machine sets a threshold brightness, so it doesn't remember everything that's in here. It only remembers the brightest spots. It picks out the brightest spots. It's actually done something really fundamental there. It's taken a grayscale image and turned it into a small set of dots. This is very easy for a computer to deal with these few coordinates. You then, around the red, set up a search area in the second frame. So you move on a frame, you say, thing on the right is what I'm looking for. The red box is where it was, so I'm going to look around it, and I'm going to move around it like that in order until I find the thing that looks closest to this. You then identify where that pattern has moved to. So it's gone from there to there. Can somebody switch off the microphone again? I think I might have muted it. I'm not sure. So you can then track that single little chunk of muscle around the place. And this is what you get. So you end up with this kind of image of all these dots lying on top of the myocardium. And each dot is a kernel tracking the myocardium underneath it. So you can see in the, pick a segment, basal septal segment, there are 3 dots across the width of it, so you can track how it thickens and thins. And there are 6 or 7 dots up and down the length of it. So there's a lot of dots in each of the segments, and the color of the different segments is just to help you identify which segments which, one's red, one's blue, and so on. So lots of dots within each segment, so a huge amount of information here. But you're now able to track the motion, the position and the motion of one kernel, which will tell you about position and speed, or 2 kernels, which will tell you about contraction, that is strain, and how quickly the strain is happening, which is strain rate. So you get all the myocardial properties out of this. Myocardial mechanical properties out of this. And then you can take this with the frame rate of the grayscale image, which is 40 or 60 or 80 or whatever, and you can after the patient's gone home, you can draw this information out of them. You can draw displacement position time graphs, you can draw speed time graphs, that's like the SE prime A prime waves you've seen before. You can see they've made, for each of these, they've made color anatomical M modes, and you can see they're symmetrical, telling you that these are probably normal. You can measure something that you definitely couldn't have measured before, which is movement in this direction. So in a parasternal long axis view, you can now measure the contraction and relaxation towards the apex, which you definitely couldn't have measured with tissue Doppler because it's the wrong direction. You see things like the strain in the long axis direction, which is what this is measures. So the strain, which is the contraction, as the heart contracts during systole, it gets shorter. Something getting shorter has got a negative strain. So that's why you see the curve goes down. At the end of systole, it's as shorter as it's going to get. So the myocardium is shortest, and then diastole it starts to lengthen again. You can see that here. Here's the R wave. At the R wave, it starts to shorten. So the strain becomes negative, typically down to about -20%. And then after the T wave, the heart starts to relax and it gets longer again during diastole. So that's typically what long axis strain looks like, a curve something like that. Transverse strain, or radial strain, that is strain across the myocardium, does the opposite, because as the heart contracts, it doesn't get shorter, it gets longer because the myocardium thickens. So it does the opposite thing. The curve goes the opposite way, it goes up rather than down. This is not global longitudinal strain. This is strain in each segment we're talking about at the moment. So as you can see, for each of the segments, as it contracts, the myocardium gets thicker and then gets thinner again, and it gets its thickest again just at the end of the T wave, where it's at the end of systole. So this is the curve shape for radial strain, which is the other way up than longitudinal strain, because longitudinal strain gets smaller, the ventricle gets smaller in the longitudinal direction, gets bigger in the radial. The myocardium gets bigger in the radial direction. And again, a symmetrical color anatomical M mode image. strain rate, that's the velocity first. So velocity, sorry, it has got the same picture as S wave, E prime wave, A prime wave, and this is strain rate, which looks like a velocity curve upside down, and the S wave going the wrong way, the E prime wave and A prime wave going the wrong way. You won't get asked about strain rate, I'm sure, in exam. And I've seen those. Okay. Since somebody asked about global longitudinal strain, I will just global longitudinal strain is a really simple thing, and if you take longitudinal strain, this is the segmental approach to it, and the global longitudinal strain. So you, segment by segment, you can see the strain in each segment. This white dotted line is the average for all the segments, and this represents, so the global longitudinal strain is just the average strain for each segment, strains for each segment averaged. So it represents the average of everything that's happening in all the segments, and you know, around minus 20% is normal for global longitudinal strain. It's an interesting marker that is behaves differently to ejection fractions as a measure of ventricular performance. So global longitudinal, what we've been looking at is segmental strain, segment by segment. Global longitudinal strain is just the average of each segment's longitudinal strain. But it's a helpful number, probably, and it's coming more and more into clinical practice. I think I'm going to get asked a question about this. You might well be asked a question something like this. You know, before you can interpret any echo measurement, you need to make sure the right measurement has been made. And you can see here, for example, that this set of dots is not tracking the myocardium. It's tracking some reverberations in here, isn't it? Rather than the myocardium, it's tracking this thing just at 3 o'clock here, the bright reverberation. And you can correct that by literally just taking your mouse and pulling it out of there and onto the myocardium. And then the right-hand image is being corrected and pulled out of the reverberation. So the left-hand image would give you the wrong answer, give you the wrong curves. The right-hand image would give you the correct curves. So if you do get a question about strain imaging, it shows you the source image like this, look at it and make sure that it's tracking the right thing. So here it wasn't tracking the right thing. It's tracking that bright reverberation. Here, if you just looked at this, you might say the strain is 10% and something even lower at the apex here. So there's clearly abnormal strain in the lateral wall. If you just looked at the right-hand image, you look at the left-hand image, you can see the reason for that is there's just, you can't see the myocardium there, so it's not tracking it because there's dropout. So again, an example before you come to a conclusion about what the measurements mean. If you're shown the image where it was taken from, look at that to make sure that's not where the abnormality is. Again, I mentioned this just because it comes up specifically in the syllabus. We talked about, you know, long axis strain and it getting to its shortest at the end of systole. Here's an example where most of the segments get to their shortest point at the end of systole, which is this green line here when the aortic valve closes, or the end of the T wave, whichever you like. You get to the end of the systole, but this one, this yellow line, continues to get shorter after systole. And that's something called post-systolic shortening. And you don't need to know anything about it apart from that is something which you see in ischemic myocardium. So post-systolic shortening, shortening happens after the end of systole, and shortening continues after the end of systole, and it's something that happens in ischemic myocardium. Isovolemic acceleration. Again, I mention this just because it is mentioned in the syllabus. It's never cropped up, and I don't think will crop up. But So this is tissue, tissue Doppler curve. This is E primed first, then A primed. Then there's this thing that happens during isovolemic contraction, and then there's the S wave, and then there's the isovolemic relaxation. There's another E primed wave. So looking during isovolemic contraction, that's the time that the heart is building up pressure to start to move. You often see a short, sharp spike before the S wave. And that short, sharp spike has got an upslope. And the upslope of that short, sharp spike, as the ventricle starts to build up pressure, the gradient of it is called isovolemic acceleration. And the relevance of isovolemic acceleration is it may be something which is not load dependent. So it might be a load independent measure of ventricular performance. Clinically, it's almost impossible to measure. Unless you've got a huge amount of experience in tissue Doppler, you won't measure accurately, and it's not got any place in clinical practice. I mention it only because it's specifically mentioned for some reason in the syllabus. So that's what it is. It's that spike just before the S wave, and it's the upslope of the spike, and it's at the time when the ventricle is starting to build up pressure. You don't need to know any more than that about it, I don't think. So the good points about tissue Doppler, about speckle tracking are: you can measure sideways motion as well as up and down motion. It's not from velocity. It's easy to acquire because it comes from standard images. There are some problems in that. Of course, the pattern changes because things move out of plane, because there's a change in the configuration of the myocardium as it changes size and so on. But actually, frame to frame change is small, but it's still a statistical process because you're looking for the closest match to that pattern as we described. So it's not really quite the truth that you think it might be. Torsion and twist we'll talk about tomorrow. Look out for artifacts, and you need to have enough frame rate compared to the heart rate so that between frame 1 and frame 2, the thing you're interested in doesn't move so far it's outside your search area. So you can't do it with very high heart rates. It doesn't work well. Okay, that's most of what you need to know about. That's most of what you need to know about deformation imaging. There are some questions on it tomorrow. I'm going to stop just for a second to get myself a glass of water. So if we take 2 minutes, I'm just going to grab a glass of water and I'll be right back, and I'll start talking about left ventricular function. If you've got any other questions, you can put them in the question box.